We physicists have hung tight for quite some time, starting around 1916, for this. The photo is of a nearby black hole, which may very well be one of the most enchanting and perplexing phenomena in the universe. Black holes are massive beasts in terms of gravity, yet they remain elusive to us. A black hole weighing perhaps 2 to 4 million times the mass of the Sun has been the subject of intense research over the last 20 or 30 years. We've gone from knowing virtually nothing about black holes to understanding significantly more, especially about those nearby. Recently, things have gotten even more exciting. Scientists from Michio Kaku recently announced that we've finally gotten a glimpse of what's inside a black hole. This new data sheds light on the details the world of science might have overlooked. Join us as we dive deeper into black holes and uncover what's inside. Space. Enormous and mysterious. What are black holes? Before we delve into the specifics of what Michio Kaku discovered, let's cover the basics. Although most people have some idea of what black holes are, there are still gaps in our understanding. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, black holes were purely theoretical. It took another 50 years for established researchers to find evidence that black holes actually exist. This happened in the 1960s when scientists were studying the star Cygnus X1, a celestial body. They observed an unusually bright blue star emitting X-rays. This star was not a dead object but was orbiting a massive dark entity. Upon further examination, it was discovered that the X-rays weren't just moving randomly. They were being sucked into this dark entity. Thus, the term black hole was coined. This discovery was groundbreaking because it provided evidence that black holes are real and not merely products of Einstein's imagination. Cygnus X1. The first black hole. This first black hole, Cygnus X1, is located in the Cygnus constellation, approximately 6,000 light-years from Earth. It was no small discovery. Cygnus X1 is over 10 times brighter than the Sun and incredibly dense, giving it a powerful gravitational pull. The gravitational pull is so strong that even light cannot escape it, hence the name black hole. The concept of a black hole is both fascinating and terrifying. It is a region in space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole is pulled in and lost forever. Searching for more black holes. After the discovery of Cygnus X1, scientists began searching for more black holes. They found that there could be as many as 100 million black holes in the Milky Way galaxy alone. However, because black holes are so difficult to detect, we still don't have an exact count. There are likely a few million black holes in the Milky Way, which makes them crucial objects of study. The defining feature of black holes is their immense gravitational pull. Anything that enters their sphere of influence is compressed to a singularity, a point of infinite density. Falling into a black hole. One of the most frightening aspects of black holes is imagining what would happen if someone fell into one. The gravitational forces would stretch the person into a thin line, a process called spaghettification. This would occur long before the complete breakdown of matter. Fortunately, the nearest black hole to Earth is about 500 light-years away, which is far enough to alleviate immediate concerns. Capturing the first image of a black hole. In 2021, researchers captured the first clear image of a black hole, the M87 black hole. This black hole was photographed over several nights, and the images provided critical evidence about its structure. The scientists discovered that black holes consist of 3 layers, contrary to the common belief that they are just voids. 1. The event horizon, the outermost layer, which marks the boundary of the black hole. Once something crosses the event horizon, it cannot escape. 2. The photon sphere, the second layer where light orbits the black hole. Any light entering this region is trapped by the black hole's gravitational pull. 3. The singularity, the innermost point where all matter is compressed into infinite density. Here, the laws of physics as we know them break down completely. Challenges in studying black holes. Each black hole is unique, which makes studying them even more challenging. While they follow the same 3-layer structure, their behavior and characteristics can vary widely. Sending a probe into a black hole is impossible because anything that crosses the event horizon is pulled into the singularity and destroyed. As a result, scientists study black holes indirectly by observing the radiation they emit and the gas and dust surrounding them. This limitation forces researchers to rely on two-dimensional models to study three-dimensional phenomena. Additionally, the sheer number of black holes in the universe, combined with their mysterious nature, makes them one of the most complex topics in astrophysics. Physical science, as we probably know it, starts to unravel when we attempt to study the interior of black holes. Traditional methods of scientific inquiry don't truly apply to the investigation of black holes. However, that doesn't mean scientists haven't been busy. There are numerous theories and explanations about black holes, and with each one, things become increasingly fascinating. One of the most compelling theories about the formation of black holes is that they are created from collapsed stars. When a star exhausts its fuel, it can no longer produce enough energy to counteract the force of gravity, which constantly pulls inward. The star begins to collapse in on itself, contracting and becoming denser. If the star is massive enough, this process can continue until it transforms into a singularity. To understand the nature of black holes, NASA scientists turned their focus to the center of the galaxy M87. Astronomers observed a massive whirlpool of extremely hot hydrogen gas spinning at an astonishing speed of 1.2 million miles per hour. The sheer force of the rotating gas disk should have caused it to fly apart, but it didn't. Scientists concluded that there must be a massive mass concentrated at the center of the galaxy to prevent this from happening. This colossal object, weighing as much as 2 to 3 billion suns, was most likely a black hole. Yet, that doesn't seem to be the only theory about black holes. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a rotating black hole. He demonstrated that a rotating black hole wouldn't collapse into a point as previously thought, but would instead form a ring of fire or a thin disk. The disk would spin so rapidly that outward forces would prevent it from collapsing. This spinning disk of matter is known as the ergosphere, the region surrounding the black hole where the laws of physics start to break down. The most intriguing aspect of Kerr's model was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical passage through spacetime that connects two separate regions of the universe, or even two parallel universes. The idea is that if someone were to fall into a black hole instead of being crushed into nothingness, they would be sucked down a tunnel through the ring of fire and ejected from a white hole into a parallel universe. To understand how this works, we need to examine the concept of spacetime in Einstein's theory. The reality we experience isn't made of separate elements but is interconnected, forming a four-dimensional fabric known as spacetime. Objects with mass warp this fabric, creating a gravitational field that pulls other objects toward them. Now imagine a sheet of paper representing spacetime. If you mark 2 points on the paper and draw a line between them, this represents how objects travel through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole, a shortcut through spacetime that connects two distant points instantly. Wormholes aren't just a science fiction concept. They are, in fact, a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse quickly. However, the existence of an Einstein-Rosen bridge would mean that black holes aren't just massive vacuum cleaners but could also serve as tunnels to different areas of spacetime. So, could we use a wormhole to travel through existence? Unfortunately, the answer is probably no. Not yet. Even if we could stabilize a wormhole, it's unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is the hard limit for how fast anything can move through spacetime. Nevertheless, the theory of wormholes and black holes as pathways to different parts of the universe, or even different times, has been a subject of fascination and speculation among physicists for a long time. The possibility that there might be shortcuts through the fabric of spacetime, allowing travel across vast distances or even into the past, could be revolutionary if we could achieve it. One of the most exciting ideas in this field of study is the Kerr wormhole, named after the mathematician who first described Einstein's equations of gravity. This type of wormhole is essentially a theoretical tunnel through spacetime that could connect two distant points, like two different universes or even two distinct times within the same universe. The Kerr wormhole is ring-shaped, like the mirror in the story of Alice in Wonderland, and could theoretically transport a traveler to another universe or era where the laws of physics might be entirely different from those we are familiar with. However, while the possibility of wormholes for interstellar travel or time travel is certainly exciting, it's also a subject of debate among physicists. Some argue that wormholes and black holes might be unstable or too dangerous to traverse due to the extreme radiation and subatomic forces surrounding their entrances. Critics point out that Einstein's equations of gravity, which are used to describe wormholes and black holes, only work for gravity, not the quantum forces that govern radiation and subatomic particles. To fully understand these phenomena, a new theory is needed, one that unifies the laws of gravity with the quantum theory of radiation throughout the universe. This is known as a theory of everything, a single framework that combines Einstein's theory of gravity and quantum theory. Michio Kaku, a renowned theoretical physicist, has been working on a theory of everything for decades. One of the most promising candidates is string theory. String theory combines gravity with quantum theory. It suggests that subatomic particles are actually tiny, vibrating strings and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a string. One fascinating aspect of string theory is that as the string moves through time, it warps the fabric of space around it, creating black holes, wormholes, and other remarkable solutions to Einstein's equations. These hidden dimensions, theorized by string theory, might hold the key to explaining the most puzzling phenomena in the universe, such as the behavior of black holes and the existence of wormholes. Some physicists believe that by uncovering the secrets of these extra dimensions, we could develop technologies far beyond our current capabilities, potentially even stabilizing wormholes for practical use. One of the major challenges, however, lies in testing these theories. The scales at which string theory operates are so minuscule, on the order of the Planck length, about meters, that current technology cannot directly observe them. Despite this, advancements in particle physics, such as experiments at the Large Hadron Collider (LHC), offer glimpses into the fundamental nature of the universe. By smashing particles together at incredibly high energies, scientists hope to detect phenomena that align with string theory predictions, such as the production of miniature black holes or evidence of extra dimensions. If string theory or some other theory of everything proves correct, it could revolutionize our understanding of the cosmos. For instance, it might offer new insights into the origin of the universe itself. Some theories suggest that our universe could be one of many in a multiverse, each with its own unique physical laws. Wormholes, in this context, might not only connect distant points within our universe but also serve as bridges to entirely different universes. The implications of such discoveries are staggering. Imagine a future where interstellar travel is not limited by the speed of light, where wormholes provide shortcuts to distant galaxies, or even where time travel becomes a reality. While these ideas currently reside in the realm of theoretical physics, history has shown that today's theories often pave the way for tomorrow's breakthroughs. However, with such potential comes significant philosophical and ethical considerations. If wormholes could connect different points in time, for example, the concept of causality, where cause precedes effect, might break down. This raises profound questions about the nature of free will, the possibility of altering the past, and the very structure of reality itself. Furthermore, the ability to traverse vast distances or even access parallel universes could introduce unforeseen risks, from disrupting cosmic stability to encountering entirely unknown forms of matter or life. Despite these challenges, humanity's pursuit of understanding continues. As physicists push the boundaries of knowledge, they remind us that even the most mind-bending concepts, black holes, wormholes, extra dimensions, are grounded in rigorous mathematical frameworks and empirical investigation. The journey toward a unified theory of everything is far from over, but every step brings us closer to unraveling the mysteries of the cosmos. In the words of Carl Sagan, somewhere, something incredible is waiting to be known. The study of black holes, wormholes, and the fundamental nature of reality reminds us of the boundless potential of human curiosity and imagination.